So we're going to look at some of these definitions. We have pre-order, partial order, strict partial order, total order, equivalence relationship. And in order for a relation to be pre-order, that relation has to be both reflexive and transitive. But if that relation is reflexive, transitive, and antisymmetric, then that means that it would be partial order. If it's strict partial order, it will be irreflexive, it will be asymmetric and transitive. If it is a total order, it will be partial order, basically meaning reflexive, transitive, and antisymmetric. But then also it will be covered such that for every two values, it is either going to be x, r, y, or it's going to be y, r, x. And I'll touch on that in a moment. But finally, we have equivalence relation. That's just going to be reflexive, symmetric, and transitive. Okay, so getting back to what I was saying about total order, all that means is we have all these properties here, but then also for every value that you can think of x and y that is within the set of numbers that you're looking at. So for example, here, we're going to be looking at this set right here where we're looking at the natural numbers, which is 0 all the way up to infinity based on the definition given to us by our professor. It can be 1 to infinity. It just depends on who is defining it and what your purpose is. But here we're going to say that it's 0 all the way up to infinity, and it's going to be every whole number. It's going to be 1, 2, 3, so forth. And the relation we're going to be looking at is this less than symbol. So for example, 3 is in fact less than 7. And all this is saying right here is that for any values you can think of, any two values, x and y, it will always be the case that we have this relationship. You cannot think of a single x or a single y such that either x is less than y or y is less than x. And that is the case. I mean, it doesn't matter what your value is. If you have 100 less than 3, that might be false, but we said this is this or that. So we have 3 less than 100. So we have 3 less than 100. Both of these numbers are in the domain. Both of them are covered by this relationship. All we need is for one of these two things to be true. This one is true. So therefore, if we can say that about every single number that is in the natural numbers, then we can say that this relationship of less than is a total order. But it also has to be reflexive, transitive, and antisymmetric. In this particular case, it is not reflexive, because if we have 3 less than 3, remember, if you've watched the last, few videos I've done, reflexive means x are x, which means that the number is a relation upon itself. So that means that 3 is less than itself, which is not true. It is false. So therefore, this is not a partial order relation. Therefore, it cannot be a total order relation. However, it does have this totality of x r y or y r x. But in order for the relation to be any one of these orders, it has to satisfy all of these conditions. So we do want to figure out, what is this? Where we have, the set of natural numbers, and we have the relationship where x is less than y, and x and y are both within the set of natural numbers. And without actually going into a proof quite yet, we can probably think about this. We know it's not reflexive because 3 less than 3 is not true. So right off the bat, we know it's not pre-order, it's not going to be partial order, and it's not going to be total order. And it's not going to be an equivalence relation. Now, I would say by process of elimination, it's strict partial order, but it is possible that it's not any of these. So therefore, we need to actually look at all the different possibilities. But we do know that it can't be any of these because it doesn't satisfy this property that is required for it to be pre-order or partial order or an equivalence relation. So let's look at what we have left. We have a strict partial order, irreflexive, basically meaning for all cases, it is not the case that x are x. And for the record, if something is reflexive, it cannot be irreflexive. And if something is irreflexive, it cannot be reflexive. And if you look at the definition of the two, this is the definition of reflexive, and this is the definition of not reflexive. They completely contradict each other. They are mutually exclusive. But again, we're not doing a proof quite yet, but just think about it. Is it true that for all values, it is never true that x is less than itself? Because x is equal to x, therefore this cannot be true. We just know that. We don't actually have to do a proof in order to know that implicitly. The next thing we want to look at is it asymmetric? Asymmetric means that x r y implies not y r x. So basically what that means is if x is less than y, then that means that it is not the case that y is less than x. Or another way to write this, because we have a not symbol, we can reverse this and we can say that x is less than y, implies that y is greater than x. That y is greater than or equal to x. And it is important to note the equal sign here, because here we're saying that y is not less than x, but we can't really say for a fact that y is not equal to x. All we know is that this is not true. And then we can plug in some random values. Again, this is nothing like a proof. But if we say, okay, 4 is less than 7, is it true that 7 is either greater than or equal to 4? And the answer is yes, it still holds. So we have a pretty good reason to believe that this is irreflexive and that it's asymmetric. And the only other thing we want to know is it transitive? Meaning that if x are y and y are z, then that would imply that x is rz. And again, we can pick some random numbers. Again, this is not a proof, but we're kind of thinking it to ourselves. Is it possible or even likely that this is the case? Now note, we need a number where x is less than y and a number where y is less than z. And we have, many options to pick from. I'm going to say that x is 3, y is 5, because x is less than y. And then we need a number, and z can be anything that is bigger than y, so we can have 7. Does that imply that x is less than z? And if you look at this, it does kind of make sense, right? So if we're saying that 5 is bigger than 3 and that 7 is bigger than 5, then it stands to reason that 7 is going to be bigger than 3. So we don't have any proof, but we have a lot of reason to think that the less than relationship on the natural numbers will follow a strict partial order. However, in order to prove that it is a strict partial order, we have to prove all 3 of these properties. So I'm going to go ahead and make up more room here. And this is the same process no matter what relation you have. So I'm only going to do this one example, but the steps are all the same. So I've written these definitions on the left here just to remind ourselves what we're trying to prove. And we want to prove this for this relation where we're looking at any pair of natural numbers and we want to look at the binary relationship less than. Now there's another way to formally write this definition, and it is important. And this is basically saying the set of all a, b, which are elements of n, such that when we have b minus a, we end up with an element in the positive integers z plus. That's not a 2, it's a z, but close enough. Basically saying that when we take our numbers b minus a, we always end up with a positive integer. And if you think about it, if we have 2 random numbers that are in the natural numbers like 4 less than 7, and this is a true statement, right? This is our a, this is our b. When we have b minus a, we are always going to end up with a positive number, a positive integer. In this case, we would end up with 7 minus 4 is equal to 3. But for something to be less than, there always has to be a leftover number that is either 1 or higher. If we had the case where we had a is 4 and b is 4, then we would have b minus a is equal to 0, and that would not be part of our set of positive integers. And that makes perfect sense because 4 less than 4 is not true. The first thing we want to prove is that it is never true that x has this relation with itself. And we, know for a fact that x is equal to x, and as such, we know that x minus x is always going to be equal to 0. And that's the fact that we already know. Any number minus itself is just going to be equal to 0. However, 0 is not an element of the positive integers. This is not the case. Therefore, it is never the case that x minus x will produce an element of the positive integers, which we have up here as our definition of what it means to be this relation. So therefore, x minus x can never be part of this relation. As such, we have this case that it is not x are x for all x, which are elements of the natural numbers. Thus, our relation is irreflexive. Now make sure that when you write your proof that you explicitly state that this is the case and point out that this is going to be equal to this, because they are the same thing, it just needs to be very apparent. In fact, I'm going to go ahead and practice what I preach and write that out here. The next thing we want to prove is that the property is transitive, and I'm going to do a proof by contradiction. So we're going to assume that our relation is not transitive. That means that there exist 3 elements in the natural numbers such that x, y, and z. So there exist an x, y, and z that are elements of the natural numbers such that we have x, r, y, and y, r, z, but we do not have the x, r, z. Because again, remember that both of these need to be true in order for this implication to be proven false. And I also want to point out that xry and yrz from our definition is written as, and by our definition I'm talking about this right here. All I'm going to do is copy this over where we have x comma y. These are elements of the natural numbers. And then we have y minus x, which produces an element of z. And we have the case that y comma z, which are elements of the natural numbers. When we take z minus y, we end up with an element that is in the positive integers. So all I've done is copy this definition over for these two terms here, xry and yrz. Well, this is our x, our y, this is our y, and our z. From this definition, what we can ascertain is y minus x is going to produce some number greater than 0. So y minus x is greater than 0. And here, same thing, z minus y is going to produce some number greater than 0. So z minus y is going to be greater than 0. And all we need to do is move these over algebraically, at which point we're going to say or that y is greater than x, or that z and z is greater than y. All I've done here is take the y minus x is greater than 0, and I've just moved the x onto the right side. It does not change the relation. Same thing here is z minus y is greater than 0. I'm just moving the y onto the right side. If you add it to both sides of the equation, you're not changing the actual relation. So what we have here is that y is greater than x, and we have that z is greater than y. And I can even rewrite that to say z is greater than y, which is greater than x. Z is greater than y, which is greater than x. However, not xrz means that there exists some x such that not x is less than z, or in other words, I'm going to write O-I-O-W, meaning or in other words. It's not at all formal. I'm just running out of room here, sorry. If we have not x is less than z, what that means is that x is greater than or equal to z. So x is greater than or equal to z. Again, remembering that all this is saying is that x is not less than z, but it doesn't say anything about it not being equal to z, so we have to include that when we flip this symbol here. But this statement is the exact same thing as this statement, and this part right here is saying the same thing as xry and yrz. And from this part, we were able to derive this right here where it says y minus x and z minus y is greater than 0, which is basically just rewritten as this right here. So I know it's a lot of jumping around, but xry and yrz basically just means this. Z is greater than y, which is greater than x. And not xrz means that x is greater than or equal to z. And this is a contradiction because we have that z is greater than all of these things, but here we have that x is greater than z. So this does not make sense. This is a contradiction. Thus, n is transitive. I wish we were done, but we are not. We still need to prove one more thing, and that this is asymmetric. So again, I'm going to leave this definition that we have here, and we're going to do the exact same thing. We're going to do a proof by contradiction. So what we're going to say is assume that our relation is not asymmetric. What that means is that there exists some value of x and y such that, again, look at our definition, x, r, y implies not y or x. All we're doing is noting this because this is the definition of what it means to be asymmetric, but we're assuming here that it is not asymmetric, so we're just adding another not symbol to it. So we have that this is going to be not x r y, not y r x. Again, I'm just copying this over from here. All I'm doing is adding an extra not to it because we are assuming that it is not asymmetric. Or in other words, what this means is that x r y implies the not cancels each other out. So that means that x r y implies y r x. That means that there exists some x and y values that are in our natural numbers here, such that, and again, I'm just copying our definition from over here over to here. We're just making sure that it applies to x and y. This is our relationship of x, r, y. Instead of a and b, we have x and y. And then we're going to have our relation of y, r, x. And instead of a and b, we're going to have y and x. So both of these cases need to be true based on what we have right here, which we're saying is our definition of what it means to not be asymmetric. But again, we can look at this and ascertain that we have that y minus x is going to be greater than 0, and that x minus y is going to be greater than 0. Because based on our definition, this is going to be a positive integer z. And we can simply rearrange this, and what we get is that y is greater than x. So from this, we get that y is greater than x and x is greater than y. And this is clearly a contradiction. This is a contradiction. And if you wanted to be more obvious about it, you could write y greater than x, which is greater than y. Again, it still does not make any sense. Thus, we can say that our relation is asymmetric.